Welcome everyone to the third event of the Robotics Today seminar series. Today we are tremendously excited to host Professor Allison Okamura from Stanford as our speaker. Before I introduce Allison, we as the organizing team acknowledge the events that are currently unfolding in the United States. We are deeply saddened by the tragic loss of lives due to racial violence. We're speaking about the lives of George Floyd, Ahmaud Arbery, Breonna Taylor, and Sean Reed, among many others. We condemn these recent appalling events, which are sadly not isolated, but represent systemic issues of racism, inequality, and injustice. We recognize that these issues are laid bare right now in the US, but can be found in countries all around the world. We stand with the protests that are happening right now in the United States and condemn the excessive police violence. The protests give us hope that we are unified by common values and that real change is possible. We created this seminar series as a means to bring the international robotics community together during this worldwide pandemic that has physically distanced us. Upon reflection, we recognize that our community is not doing well when it comes to being inclusive to diverse voices from roboticists from a variety of backgrounds, countries, races, and genders. While we have some outreach programs, for example, for women in robotics and engineering, we are lacking a broader set of measures as present in other communities. This is a shout out to organizations like AI for All and Black in AI. What can we do to change the current status quo? What can we do for the robotics community to embrace its richness? With this seminar series, we commit to diversify the voices typically heard in robotics and elevate new voices. We will actively solicit suggestions for speakers from a diverse set of institutions and organizations. We welcome suggestions for speakers from you. You can send us names using the form at the bottom of the seminar webpage. While this is only a small step, we will leverage the large attendance to the seminar series to foster a discussion about how to make the robotics community more inclusive. If you have suggestions, please also contact us through the form on the seminar website. With these words, it's my pleasure to now introduce this week's speaker, Professor Allison Okamura. Allison did her undergrad at UC Berkeley and her PhD at Stanford University, both in mechanical engineering. She is now a full professor in the mechanical engineering department at Stanford University. Her best-known work is on developing the principles and tools needed to realize advanced robotic and human-machine systems capable of touch interaction, particularly for biomedical applications such as teleoperated robot-assisted surgery. More recently, Allison worked on soft robots, a type of robot technology that I find just mind-boggling, as none of the good old robotics principles actually hold. Soft robots have abilities that are hard to or sometimes impossible to implement on traditional robots. Yet they also open up many new challenges for exciting research direction, which is what Allison is going to talk about today. So welcome, Allison.
Thank you very much. I'm going to share my presentation. Thank you all so much for inviting me here today. It's an extraordinary thing that the organizers are doing with this seminar to bring us together. And as Jeanette mentioned, coming together is even more important now in the face of the racial injustice and challenges that people inside and outside our community are seeing. And I'll actually have a few more words to say about diversity in the field of robotics at the end of my presentation. But for now, let me talk a little bit about my motivation. I've always been very interested in human-machine systems because I'm just as interested in people as I am in robots. And the field of soft robotics, as Jeanette described, is a growing, relatively new field that I think has incredible potential to help people. But it also has so many challenges that sometimes we don't know where to start. So my talk will not just describe some specific projects in my research lab, but also some thoughts, kind of a position about how we should think about soft robot design, and also thinking about applications and trying to make practical systems that can help people. So the field of soft robotics spans so many different types of robots. They can range from robots that are mostly traditional and stiff that have soft joints to robots where even the electronic components or the control components are effectively made of fluids and soft as well. And along this spectrum, you can find robots that are made soft both by their fundamental material. For example, many of the robots shown in these images are made of elastomeric materials, which are highly stretchable, 300% more or higher strain. But also you can have robots that are effectively made soft by their structure. They're long and they're thin, or they have soft joints in specific locations. And this sort of gives a design space that is quite varied and quite complex to consider. Another point is that these soft materials, the materials themselves, they can be flexible and or they can be stretchable. You can have materials that are actually quite flexible and bendable, but don't stretch. And in fact, most of the materials that I'll be discussing today are in this class, whereas there are also many soft robots made out of these stretchable elastomeric materials. And the reason we think that we would like to have robots have these soft features is adaptability to the environment. We get a lot of inspiration from biological systems, ranging from plants to animals. The potential for safety when you interact with people. A soft robot might be lighter weight, therefore lower inertia upon contact, and have less sharp edges. And then finally, although not always true, there's also the potential to reduce cost with these soft robots. And this will also get to issues of accessibility I'll discuss a bit at the end. So when we look at what are the advantages of hard robots and soft robots, and what are the fundamental structures, of course, there are many different types of robots, but let's think about your traditional serial chain manipulator type robot here. In a hard robot, you have these localized joints, which can swing quite a bit in various directions, but you have these stiff members, the linkages. Soft robots tend to be more of a continuum nature, that is, they curve over a large space, which can give them challenges with achieving particular workspaces with their tips, but do allow them to navigate through environments, perhaps in a more elegant and smooth way than a traditional hard robot. So to give examples of this, the localized joints of hard robots, they allow sharp turns that lets them sometimes get places where a soft robot might not be able to go if it doesn't have the ability to curve sharply at a particular location. On the other hand, the bending and the softness of a soft robot will allow navigation that is perhaps safe for both the robot and the environment when you're operating in cluttered areas. And the thing that I would like to be pushing a bit towards the end of this talk, not that it's something we've fully achieved yet, is that we could get the best of both worlds by having soft continuum members and also localized joints where they're required. And we'll start to see some movement towards that in some of the more recent work. So the focus that I'll have in the field of soft robotics is continuum robots. And these are characterized by long, thin members and are typically associated with manipulation tasks. Of course, there are many other types of soft robots, and also many more continuum robots than what I've cited here. But this gives an example of the types of systems that have been built by researchers all over the world in order to get this kind of continuum behavior. Some of them being classical soft robots, others actually incorporating joints and pneumatics. So the types of projects I'll be discussing today, I'm going to pick out three in particular, and I'd like to think of them as a continuum of continuum robots. And the continuums that I'm talking about are, first of all, in material. So in these three projects, I'll be looking at devices where the material is inherently relatively stiff versus the other two examples where the material is relatively flexible. But we're also going to look at the ways in which these materials are used within a structure. In a case where the material is very stiff, the only way in which the robot becomes soft is by the structure and the shape of it, allowing it to be flexible. You can have also robots like the middle example, where the material and the structure is flexible, and cases where, although the low-level material might be flexible, they're arranged in a relatively stiff structure. And all these examples will hopefully enlighten some of the advantages of soft and hard along the way. And I'm going to start with a project that's a few years old now, but I think is a nice context for this area of work, which are soft, steerable, patient-specific medical robots. And the motivation for this type of research, again, thinking about the humanitarian aspects, how do we actually create soft robots that are useful for people, is that we can compare this to existing clinical devices, such as this teleoperated Da Vinci surgical system, which is useful in many medical procedures, but you could kind of consider it to be a template surgical system, in that you have a relatively limited set of tools and instruments, and much of the way the operation is done has to be adapted to the robot. And a challenge, a humanitarian challenge for these types of systems, is that there are many marginalized patient populations that cannot actually take advantage of these kinds of robots. Examples are children whose anatomy is quite different from that for which the robot was designed, as well as obese patients or other patients with comorbidities where access actually requires more adaptability and flexibility than what traditional robotic manipulators allow. So in order to think about making this more patient-specific design, how do you make a personalized robot for someone who needs to have a surgery? We start with the person. And the data I'll show in these examples actually comes from a 9-year-old boy who had a kidney stone. This particular picture is actually my own 9-year-old son, not the patient from which the data was taken. In this picture, he's doing his favorite shelter-in-place activity, which is playing Minecraft on the iPad. We're working on that. But what I wanted to communicate here is that when it comes to medical robots, these are real surgeries on real people, although not in this particular case. But what you do when you start this kind of procedure is you perform a scan of the patient, in this case, a CT scan that identifies the location of the lesion, or in this case, a kidney stone. And then you can develop a 3D model of that specific patient. And these images may look different from ones that you have seen before, because most of the image you see in the past are probably from adults, whereas this one is from a 9-year-old boy for whom a Da Vinci surgery wouldn't have been the right size. And then what we're interested in is having this data, this amazing information from the images of the patient in order to go through a design process. And in that design process, the surgeon now becomes a designer of the patient-specific robot that we would like to use. So this is an interesting thing for me as a mechanical engineer. I think if you were a mechanical engineer several decades ago, you would probably know very well how to fix your car. I frankly don't know how to fix my car, in large part because cars are so electronically controlled that they are closed off to the user, even to an expert. It requires very specialized knowledge and really equipment in order to do anything with a car these days. So in the same sense, surgeons are now cut out from the design process of the surgical instruments that they use. And so we would like to bring the surgeon back into the design loop and give them the tools to do that. And this is something that we can do in a patient-specific design workflow. Once the surgeon, and I'll talk more in a minute about how this is accomplished, but once the surgeon has come up with their desired design, we fabricate the components of this relatively soft robot, and then we drive it using a robotic base that can be used to control the device as it goes into the patient. So let's talk about some of these components. First, I think it's important to discuss the type of robot itself. You could probably go through this process with many different types of robots, But what we've used are concentric tube robots. The images here are shown using nitinol, which is not being used for its shape memory alloy properties, but rather because of its super elasticity. And that is the nature of softness in this system. This super elasticity allows these pre-curved tubes to be inserted and spun with respect to each other in order to create this tentacle-like behavior that you can hopefully see in this video, although I'm sure it's a bit choppy over Zoom. Now, in this kind of system, I should note that it was inspired by previous work on steerable needles, which were designed to go through tissue. In this case, concentric tube robots are designed to go through lumens or work in open space. And there's been pioneering work on this type of robot from Bob Webster and people from Pierre Dupont's group and many others as well. So given this type of robot, we have this design process that I mentioned allows the surgeon to be in the loop. So my former PhD student, Tanya Morimoto here, is demonstrating selecting a set of points where she would like her continuum robot to go. And then the concentric tube robot is automatically designed using some somewhat complex kinematics, given the fact that the bending of this robot occurs through material interactions of the various tubes. And she's demonstrating how it can be moved around. Now, normally in this design process, what Tanya would be doing is designing the robot inside in 3D of the model of the patient, but actually in a 2D video presenting to other people, it's really hard to have situational awareness. So here she's designing the robot and checking it outside of the virtual patient body. So once that design is initialized, it can also be optimized either through manipulation by the clinician themselves or by an automated system. And this is actually a choice of the amount of automation versus human-controlled design. And you can simulate the robot afterwards and make sure that it's not moving and hitting, for example, soft tissues that you don't want it to make contact with. So after this process, we've designed this and tested this, obviously, with people in the lab, but it is really critical that clinicians can use it. So this is one of our clinician collaborators, Dr. Shea, who is a pediatric urologist who actually got us the scans of the patient, the 9-year-old boy that we were trying to design the robot for. All right. My computer seems to be hanging a bit, so I'll talk a little bit more about this and see if it recovers. So once you go through this process of designing the robot, we then 3D print it. While I mentioned earlier that nitinol has been used as the material for many of these concentric tube robots, and it has a lot of great advantages, processing nitinol is actually relatively challenging. Nitinol itself is, because of its super elastic nature, requires very large heat and or voltages applied against it in order to set it. But PCL, a 3D printed plastic, which is also biodegradable, can be simply printed on a MakerBot. And so this can be done in the lab. They can also be sterilized, and this can be used to make the tubes, and it can kind of be made to order right after the design process occurs. And once that happens, it can be integrated into an actuation system. In this case, we took advantage of the flexibility of 3D printing to create a somewhat novel waffle gear approach to insertion and spinning of each of the 3 tubes, and demonstrated that you can make this compact, lightweight system handheld, mounted on the base of another surgical robot like a Da Vinci teleoperated robot, and that you can reach targets within a few millimeters, even without closed loop control. So this is with open loop, just using the kinematic models applied to these concentric tubes. And in practice, I should say it's unlikely that the system would be run autonomously. It's going to be teleoperated for safety, much as current teleoperated surgical robots are done. So what we've been able to do is not yet apply this to patients. That is still coming, but we've actually effectively 3D printed a 9-year-old boy patient at the relevant organs based on the models that we had originally. So we can identify various components like the liver, the kidney itself, and the tumor located in the kidney. We can model this, and as well as the obstacles that we have to go around, like other organs and the ribs in this case. So what we can do is use an off-the-shelf haptic device as a master manipulator, and we can control the different degrees of freedom. I won't be talking about it much here, although an important future work for soft robots and ongoing in many research groups is how do you control the many degrees of freedom of such a robot? What is the right human interface if you want to teleoperate it? And in this case, we had various tubes and buttons that are actually akin to many surgical robots that are used today. So we've been able to demonstrate this in terms of going around different obstacles and reaching targets. But as you can see, due to the nature of this robot, going back to my point earlier about not being able to make sharp turns, this type of concentric tube robot, while being very thin, because the actuators are all off board at the base, and so what goes into the patient is very small, we still have this limitation that we cannot make very sharp turns, and that actually creates some limitations to its possible workspace, as you can imagine. So what we're going to start to do now is explore some other types of robots where we start towards being able to make sharp turns on soft continuum robots. And the first example of that is a set of robots that grow by tip eversion. And what I mean by tip eversion, well, first of all, let me say what I mean by growth. What I mean by growth is systems that effectively extend their length, not by just being pushed in the way a needle might be, but rather by actually adding material to the tip. There are many things in nature that do this, and as shown in the bottom picture here, vines, which is why we call these vine robots, has been a great inspiration for us. So one of the ways in which you can extend the tip of something and have it still be a soft robot is through a process called eversion. So in this somewhat hiccupy video, hopefully you can see that we have a soft plastic material akin to the material of a Ziploc bag formed in the shape of a tube, and new material is fed through the center, which everts or flips inside out at the tip in order to lengthen. And if you're having trouble picturing how this works, perhaps you've played with a water snake toy. They're really fun. These are basically elongated toroids. And in fact, some people have made robots like these water snake toys. I think Mark Yim, who's a visitor today, a guest panelist today, has made such robots. In our case, though, rather than making a toroid, we simply want to grow ours as long as possible. And so we keep extending the tip rather than having it flip back to the base. And this growth can happen extremely fast. So here are a few more videos which demonstrate how this actually is achieved in a system. How do we make this a deployable concept? Well, you can create a spool of this thin-walled plastic material in a tubular shape, put it in a pressurized air chamber, flip over the top in an eversion, and then apply air pressure, which will cause it to grow. And when you do this, you can create unsupported vertical growth, as shown in the top right video, until eventually it buckles and falls over. But it's a pretty amazing extension given the softness of the material. And it's also possible because it's somewhat lightweight. And then when it's on the ground, it can really go on until basically you run out of plastic, which is what happened in this case. So here we're seeing the spool unwinding from a very compact package at the base. And on the right, we're sort of walking the path that the robot followed. In this case, I should say, though, is it really a robot? It's really just a plastic bag filled with air that's being pressurized and going wherever it wants to go, following the favorite moniker of soft roboticists of embodied intelligence. But hopefully you can see in this video that it has managed to snake its way through some interesting obstacles, such as a series of pipes that are about to come up, just simply by bouncing off of the obstacles in the environment and continuing to want to grow. And these are the pipes right here, at least on the video, part of the video that I'm seeing. So how do we make it a robot if this is simply a plastic bag filled with air? Well, you need to be able to steer it. And controlling the direction of growth can be done using many different mechanisms. Our group and other research groups have tested various mechanisms. And some are permanent, which can actually be a little more efficient in terms of space and weight. But for the most part, you would like to have reversible direction change. And for that, we've built on some work done at MIT with pouch motors. And we've created series pouch motors, which are now mounted along the side of the robot and basically act like pneumatic tendons in order to shorten the length along certain sides of the robot. And this is reversible. And it's also a soft actuator such that it doesn't impede the eversion process and the robot can still grow. So when you combine this ability to have pneumatic actuation for steering as well as growth, you have this powerful ability to reach to targets in your workspace in what some people seem to think is a pretty creepy pseudo-biological behavior. And all of the videos shown here are actually autonomously controlled based on a camera that's mounted on the tip of the robot. And although, of course, see shortly that such robots can be teleoperated as well. And for many humanitarian purposes, we will want to teleoperate the robot because we don't yet have the situational awareness to fully control a soft-bodied robot in many environments. So I want to point out that this pneumatic actuation method with series pouch motors is not the only way to control growth direction or steer it. Another is through tendon routing, which does have advantages in terms of larger forces and being able to achieve larger curvatures. So this is where this idea comes in that we need to have sharper turns in our soft robots in order to reach a desired workspace. And while these are not 90-degree turns, it's much tighter of a turn than what we can achieve with a typical pneumatic type actuator. And if anybody is interested in how we've used these types of actuation in order to make antennas that change their shape, that's actually an RAL paper that also has a presentation at ICRA from my postdoc, Laura Blumenschein. So what are the applications? I think the most exciting thing for me about this project, although I get pretty geeked about the mechanism being kind of interesting, is that there are some really interesting applications. These robots can get into places where even many other soft robots can't go. They can go through rough environments and even be punctured, but still keep going because the material doesn't slide with respect to the thing that poked it. And so whatever poked it effectively fills the hole, and so it doesn't leak too much. And then you can do things like deliver sensors through the tip. One of my favorites is the video on the upper right, which is our firefighting version of the robot. Remember that these robots are extremely cheap. They're basically plastic bags filled with air. And so if you would like to fight fire with it, you can put a mix of water and air inside, pressurize it, and then the fire will melt the plastic and the water and air will come out at the desired location. All of the examples on this slide are pre-formed robots. That is, we've basically used tape in order to shorten the plastic in certain areas in order to have it achieve some desired shape based on what we know in the environment. And that's also the case in this lower left video where we're doing a simple manipulation task of growing around a valve and then pulling from the base in order to turn it. One of the exciting things here is despite the fact that it's a soft robot, because it's soft in terms of its flexibility and therefore it bends very easily, but it's not actually stretchable. You can pull from the base and the robot is actually quite strong in tension, maybe even stronger in tension if you run a string through the center. And so because of that, we're enabled to do this kind of remote manipulation task. The last point I want to make, which was showing on the video on the lower right, is that you can also use obstacles in the environment to help you turn. And so you can, if you're aware of the environment and you can do some planning, the robot can take advantage of its softness, this embodied intelligence, in order to achieve its goal with actually very minimal actuation. So those are all exciting applications, which many of which we think could benefit humanity in things like search and rescue, as well as medicine. And I should note that medical applications are being explored by Elliot Hawks at UC Santa Barbara and Tanya Morimoto at UC San Diego. And the other application where we put this into practice has been archaeological exploration. I'll see if I can get this video to continue playing. Great. Maybe not so great. I will tell you about it as it attempts to play. So this is something my student Margaret Code did, where she took the soft growing robot to an archaeological site in Chavin in Peru and was able to teleoperate it into very small tunnels, which previously or almost impossible to get into. And this allows you to take images and even retrieve artifacts in locations that were not previously accessible. So all of these, these examples I've given so far, most of them are about navigation, and I had one very simple manipulation task. But in order to be useful for people, we really need to think about how these kinds of soft manipulators, how manipulators can be formed from these types of soft robots. And one of the challenges that's probably pretty obvious to you by now is that it's not very strong in bending. And so my student Brian Doe has developed jamming techniques that the layer jamming that helps keep the robot stiff where desired. And so a jammed robot can be made straight if desired compared to an unjammed robot that will bend. The other cool thing about this jamming technique, or really any technique that allows you to selectively make parts of the robots more stiff versus more soft, is that you can start to achieve these sharper turns that I mentioned earlier were desirable. So for example, if you start with a long robot that has a tendon pull on one side or both sides, you can unstiffen a particular area of the robot, pull on that tendon, and then it will effectively turn or buckle at the point where you unstiffened it. And then you can re-stiffen it, pull on a different tendon, and then buckle it at a different point. And therefore, you can start to get these movable, placeable joints on the robot that starts to give you some of the kinds of dexterity you see in traditional hard robots, but still enable the sort of soft robot behaviors that we're also seeking to maintain. Now, eventually, what we would really like to do is real manipulation. That is, be able to pick up objects and move them around. You could even extend this to in-hand manipulation if you imagine multiple of these robots. At this point, we're nowhere near making these complex systems quite that small. But this involves adding grippers to the end effector, being able to control curvature versus straightness where we want to. And a couple of these are very recent works, one of them being presented recently at ICRA and others that are under review. So this is how we're starting to get towards manipulation and even being able to control the shape with more fidelity than has been achievable previously. So all of this is pretty exciting, but one of the things that I'm most excited about now is work that was very recently published about shape-changing robots that are in a truss form factor. And this word isoparametric, I'll explain what I mean by that very shortly. So these types of robots are inflated beam robots, just like the Vine robots I showed earlier. The inflated beam is the underlying component. But now we are putting this into a truss form factor. And trusses have certain advantages. So many people, this is just a small spattering of the example of prior work that's been done on truss robots, but the traditional truss robot is based on the idea that you have joints which are connected by members that extend their length. The difference for our soft growing truss robot, whose video is extremely jumpy, so you're probably not seeing it move much, is that these members actually change in length. And let's see if we can explain that better on the next slide. So one of the key goals for creating a robot that will serve humanitarian purposes and move around in our environment is that we do have to remove the tether of the pneumatic system. So many examples, of course, of soft robots, ranging from plastic ones to deformable ones, is that they all have these tethers going to the pneumatic actuator base. So for example, a compressor. And this is something that we would like to avoid. So rather than extending the members, which requires additional pneumatic pressure, so it requires more volume of air because air is compressible, we have an approach where we would like to form a truss from a single continuous member. So one inflated beam that we bend together, and instead of trying to actually extend the different lengths of the members, we take a point which forms a joint and we move that joint around. So that's the fundamental insight, is that we make the joints move relative to the structure so that you can have a constant volume, constant perimeter inflated beam, and that's where the isoparametric comes from. So in these cases, you have this joint which can slide back and forth and move relative to the structure. So this isoparametric robot, the reason why it's called isoparametric is that the pair here is not with an A, it's with an E, referring to the word perimeter. And the idea is that the perimeter of one of these inflated beams remains constant, and then the volume of air in the beam also remains constant. And this allows it to change shape significantly just by moving the joints, but not actually having to tether it and get additional air pressure. And of course, a key point here, let me go through these different components and then I'll make my key point. There's an inflated fabric tube, in this case, several of them attached together. We have roller modules which create these movable joints. And this is what I was referring to earlier in the talk about being able to take a soft robot and give it sharp turns. These roller modules are allowing that. In addition, we need universal joints that connect the different tubes together in order to get a truss-like shape. And a last point is making these roller modules is not trivial. Conceptually, it's actually very straightforward, but making it happen in the real world actually requires a lot of analysis and careful experimentation to figure out how you can travel over the tube with a reasonable amount of friction. So locomotion-wise, this truss robot can do it, and it can do it while it's untethered, which is pretty exciting. It's not the fastest robot you've ever seen, but it does allow itself to turn and rotate given these different, given the different changes of the locations of the roller modules. We also have some compliance of the overall system because the different members are inflated beams. They are somewhat soft. That said, in order for the whole device to have the structure that it needs to have to maintain a truss, they're inflated to relatively high pressure, say compared to our growing soft robots. That might just be 1 or 2 psi. In this case, you need tens or possibly even hundreds of pounds per square inch. Yet still, the robot is overall quite safe. A person can even sit inside of it and jump on top of it, as has been demonstrated by our students. The robot itself can also use its softness to help it pick up and grasp and even do a kind of in-hand manipulation of objects, as we've shown with a basketball. Another cool thing about this type of robot, if you think about the joints as being something that you can attach onto any inflated beams, is a sense of modularity. You could take something that was a 3 triangle truss robot and actually turn it in, or 3D truss robot and turn it into a planar type of truss robot, as shown on the left, or you can use just one big beam, as shown on the right, and it can change size and change its shape depending on how you've mounted and connected the various roller modules. So that's pretty exciting. And so what we're getting towards here is the best of both worlds, a robot that has some inherent underlying softness, but one that has these sharp joints that give it effectively some more dexterity, like that which traditional robots have. So these are three types of soft robots or continuum robots, again, with various properties of hardness and softness and their ability to create joints. And the applications for the first two I touched on quite a bit, the first one being patient-specific medical robots, the other one being a wide range of things ranging from manipulation to search and rescue. The truss robot is going to have applications in exploration, possibly even in space on other planets. It has advantages of when you deflate it, it becomes very small and relatively lightweight compared to other robots its size, but it can be expanded to fill up a large space. But that said, all of these systems are ones that, while there shows initial promise, there does still have to be a lot of work to make it done to be something that will truly help humanity. So I think this is a call for not just roboticists everywhere, as we know this is constantly a problem or a challenge, but soft roboticists to think about how do the systems actually evolve into something that can be practically used by human beings. And speaking of human beings, I really want to spend some time thanking the amazing people who have worked on these projects. So first of all, this is a set of folks who have been primary researchers on the projects that I just showed. And I'm first listing people who have either already left my lab and have independent faculty careers or careers at other places, as well as people who are just about to leave the lab. And I want to thank Tanya, Elliot, Laura, Joey, Ming, and Nathan for everything that they've done in our group. In addition, in our larger set of soft robot projects, I wanted to acknowledge the current students who are working on these, Fabio, Margaret, Nathaniel, and Brian, who are really carrying the torch and pushing forward this technology. And all of these folks have really deep humanitarian interests and would like to see these robots being used for good. And then faculty collaborators, Jonathan, Sean, Mac, and Jihuan, as well as some others who just, we didn't have time to talk about those specific projects here. And all of their students who I'm not able to mention, who have contributed to these projects. Working with this group of people has just been extraordinary. And then to my overall research lab group, also known as the Charmers, we're known as the Charm Lab, the Collaborative Haptics and Robotics in Medicine Lab. And the Charmers is an amazing group of people who support each other. They relish in their diverse research interests and are exploring this field together. And with that, I want to say a few things about the importance of humans in the field of robotics. Of course, it's not just about humanitarian applications, but also I think it's really important that we think about who does this research. For me, working with a diverse group of students and that diversity coming from so many directions, whether it be gender or race or ethnicity, sexual orientation, socioeconomic background, or nationality, having a diverse group of people come together and work on robotics problems, not just for funding or to write a paper, but because they would like to see how this work will impact their communities and how it will affect the lives of their children and future people throughout the world. This is what brings me to work every day. I do love robots. I geek out over the robots, but what I really love the most is the people. And I really want to emphasize how the diversity of this group is what I think allows us to do a lot of the great research that we're lucky to be allowed to do. And with that, I want to thank everyone for listening. And if you're interested in looking at more or getting a better view of our videos through our YouTube channel, you can go to charm.stanford.edu. Thank you.
All right, that's great. Thanks, Allison. That was a fantastic talk. Thanks for being so personal. And thanks also for pulling through the technical glitches with the interface, sometimes with the videos, so nicely. So I guess we're gonna transition now to the panel discussion. And very quickly, we have in the panel today, well, Jeanette, Luca, Marco, and myself, and students Mengyuan, Rachel, and Niha, which they've been paying attention and will continue paying attention to all the questions from the audience. And we have a special guest today, a special expert, which just like Allison has been coming up with unique mechanisms throughout his life, Mark Yim. Thank you for being here. He's with the Mechanical Engineering Department at UPenn and director of the GRASP Lab, and actually doing now sabbatical at Stanford. So he maybe have a inside scoop on what's going on in Allison's lab. Mark, do you want to take it with the first question?
Sure, thanks. I want to say, Allison, that was a really interesting talk there. The breadth of the types of things that you are doing is really interesting, and I love to see that. And actually, I've been told by the moderators that I have to be relatively quick. So I'm going to reduce my 5 questions to just 2, and hopefully they'll be quick. The first thing is just following up on your the diversity part, which is super important. You have this also wide range of devices and applications, and they're very different. And there's a lot of creativity going on in those types of things as you do the design. Does the diversity of the students, the people that are involved, how does it impact the design work that you do in terms of how you come up with things?
Yeah, thank you for asking that. So I think that projects in our lab are in large part very student driven. What I try to do is give as much freedom as possible to the students and the postdocs to engage in research directions that are of interest to them. And a lot of the time that means being able to pivot and start exploring a new topic, which was not your original goal. So one example is when Elliot Hawks would first develop our ideas related to the vine growing robot with Tippy version. We were at that point trying to do a completely different project and come up with soft linear actuators. And Elliot, being Elliot, probably came up with 20 different designs. And I said, that one, while totally useless for the project that we were trying to solve, is totally awesome. And if you like to explore it, go for it. Upon which he enlisted about half my lab to switch over to vine robots and start exploring that topic. This does create challenges in that you'll have to figure out how are you going to pivot funding, how are you going to find opportunities for students to do this. But to get more to your point, that this is sort of how it happens organically. But I do think a lot of the reason it does happen is because of the diversity of people involved. And some of the ideas in our lab, some of the best ones have come from high school students who intern for the summer because someone comes in with a different perspective or has not come from the same background and doesn't inherently feel or see the same constraints or even the same opportunities as other people do, that gives them a unique perspective. And we're so lucky to be in a field like robotics, which takes all comers. There are so many different types of skill sets, so many different types of ways in which people contribute to the field. You know, we know roboticists who are psychologists, we know roboticists who are computer scientists, and we know roboticists who spend all their time in a machine shop. There are so many different ways that you can contribute, and it's a field where almost no idea is bad. It's a creative field, and for that creativity to flourish, you really have to have people that are not all coming from the same background.
Thanks. I'm 100% on board with you. That I believe exactly all that stuff. But if it's okay for me, I'd like to ask a technical question.
Yeah.
Also, so this is the last question. The interesting thing about the soft robots, the extreme side, you get like an octopus, right? Very, very soft, all muscle. They can apply forces. I want to focus on forces. Question is basically on forces. I know you've shown the Vine robot like lifting really heavy objects by getting underneath them and using pressure. But I'm wondering whether applying focused forces like turning a bolt, might be slightly different in nature. If you look at animals that can apply focused large forces, they have bones usually, muscles and bones together. Do we need to have? Is there a way we can do things that are? I mean, you're talking about doing both, but bones and muscles, is that the only way, or are there other ways?
Yeah, that's a great question. There's definitely a trade-off between hard and soft, and as soon as you have bones, you may not be able to have the same type of navigation capability. And so my view is it likely will be application specific, but I think a good place to start is to say, if you do have a robot that is soft, in what directions is it soft and what directions is it hard? So for example, this idea that a Vine robot, these plastic sheets of material, they're very strong in tension, and you have the potential to parallelize them, right? You could wrap multiple times around an object, and then that parallelness also enables very large forces. But that doesn't necessarily mean that you can do that, in any direction and any degree of freedom. And so I think you have to decide where say, this is my robot, this is the set of materials I'm going to work with, and am I going to be able to channel the directions and channel the forces in the directions I need to, versus where am I going to need a new actuator or some kind of underlying hardness to the structure.
Thank you.
Thanks, Mark. Feel free to jump in anytime to ask another question or clarification. So the question that I had in mind, I think it's related to last Mark's question. And now that I'm thinking about it, maybe it is the same one, I don't know, but I'll do it anyway. So in your talk, you make an explicit distinction between material and structure, right? And I guess that is a useful distinction when we're trying to do analysis or conceptualizing sort of inventions. Where do I have to come up with a new idea for each one of those two? Is that also a limitation? Is there a point where the distinction between what is material and what is structure becomes diffuse, and there is no special distinction, especially in the context of like 3D printing techniques now that allow more flexibility?
Yeah, that's a great point. So all models are wrong, but some are useful, and maybe this is one of those models. So I do think that there's concepts like meta materials, especially, which actually kind of merge these ideas of structure and material. And in that case, it kind of flips my interpretation on its head, where you have individual components which are effectively thought of as having structure, and then together they behave like a material with new interesting properties. And I think a good example of the structural versus material kind of integrating into one would be auxetic, so-called auxetic materials. definitely there are people that develop the materials themselves that are auxetic. So these are materials, for those who aren't familiar with the term, that don't obey Poisson's ratio. And so as you push in one direction rather than expanding in the other direction, they might compress in the other direction, to put it simply. But many roboticists, really people who would call themselves soft roboticists, are coming up with different designs for structures that enable this auxetic behavior, which is thought of as a material behavior. So there's definitely counter examples, and you could certainly blur the line also through smart materials, which change their material properties, which sort of obviate the need to rely on a structure to get a certain property.
Great, thanks Alberto, and thanks Allison for the great talk and for the very interesting discussion. I have a question actually about perception and state estimation. So you were showing in the slides example in which the robot with a camera pointing to the object it has to reach can complete complex tasks.
Right.
However, of course, in general, if the robot has to navigate among obstacles, it will require complex exteroceptive and proprioceptive sensing and estimation, estimation including the configuration of the soft robot itself. So my question, I guess, is a two-part question, but my question is, what are your thoughts on future research directions for state estimation, proprioceptive and exteroceptive sensing for soft robots? And I guess a related question, which is another angle on the same question, is in which sense morphological computing, which is this capability of leveraging mechanical aspects to help the control side of things, can make state estimation, I don't know, either easier or harder, I don't know. Thank you.
Oh, that's a fantastic question. Thank you very much for asking about it. Yes, I really did not talk about sensing at all in my presentation. And that's a huge challenge and a huge opportunity. So what we've focused on so far from sensing has really been about using the robot to deploy a sensor, right? A camera just, to get an image of the environment and maybe to be involved in the control. But really the point is to see where it is that you're exploring. We're doing a project now of going into the burrow of California tiger salamanders and adding on temperature and humidity sensors. And so really the robot's purpose is to deploy those sensors. But in order to control the robot, I think this is kind of a debate that I think most soft roboticists would agree exists in the community, in that a soft robot purist might say, well, you don't need to do precise control, so you don't need to have great exteroperception or even proprioception, because the robot is just going to bounce around and wind up doing what it's supposed to do due to its embodied intelligence. Now, for a lot of practical applications, I don't necessarily think that can't really be the universal answer. So what we do need to have is, first of all, sufficient proprioception that when the robot is stuck or not growing, in our case, in the way that it should be. And then on the point of teleoperation, you'd say you need sufficient proprioception and exteroperception to give the human operator enough of a sense of telepresence, a kind of situational awareness, in order to do the control that they want to do. As you probably guessed from my talk, I'm not really a planning person, although I collaborate with fantastic people who work on those topics. And so what I typically do is rely on the human operator to look at that sensor information and effectively do that state estimation and make those decisions. But when it comes to planning in unknown and cluttered environments, a combination of proprioceptors that tells you what is the actual shape of the robot and its location in space relative to objects, as well as exteroperception that lets you know about sort of the contacts with those objects, is going to be important. And there are so many different types of sensors that creative people are exploring to do this. But at this moment, most of them, frankly, are just not yet practical to be integrated into these kinds of robots. Like, they create too many wires, they're too heavy, they need to have specialized conditions under which to operate. And we are constantly looking for sensors that we can add and have collaborators that we're exploring that with but it's very challenging. And so in large part, we'd like to see how much we can get away with without doing sensing.
Thank you. Okay. Hi, so thank you, first of all, for your very insightful talk. So far, you haven't received a controversial question yet, so it's my turn to ask you something mildly controversial. And my question is, to what extent soft robots address key application needs? Like, for example, considering the isoperimetric robot, do you see an application where these robots would represent an optimal trade-off between, among capability, complexity, robustness, and so on?
Yeah, that's a great question. Going into environments that require inspection is oftentimes not achievable with other types of robots. So I'm just going to say inspection very broadly. And this could be the search part of search and rescue. It could be going into a mine shaft to observe it. It could be going into the engine of a jet in order to do inspection. These are things that are now not possible to do with a lot of rigid robots, either because of their size, because of their mode of locomotion, like it's maybe not practical to send a drone in, or the holes are too small for even a rigid type of snake robot to make it in. And the soft robots, will be able to enter those spaces and make the kind of turns and exploit the environment and not be damaged by the environment of other types of robots. So I feel like if there's any sort of key general type of application, it would be inspection. At this point, I think that hasn't happened in terms of seeing products and application because the robots typically aren't able to carry a payload. So you rarely see soft robots carry a payload. And one of the things that, I'm not sure why it took me so long to realize this, but I feel like very recently I noticed that most soft robot grippers and manipulators, you see them pick up objects, but you never see them put them down. Like they drop them into a trash can or they drop it into a paper bag, but the ability to both pick up and have sufficient control to put something down is going to be another issue. So inspection, I think, is something that's a low enough bar to achieve because you don't actually have to manipulate something carefully. You just have to get sensors into different locations. And soft robots can do that, and they can carry sensors that are effectively really small payloads. So that's, I think, the first set of applications that are
just to press you a little bit harder on this topic. Sure. Of course, when you design a robot, you also have to take into account power consumption, so you have to bring with you a battery, so that dramatically increases the system engineering effort. And that I come from a space robotics domain, where when you start putting together all these requirements, then more complicated exotic solutions oftentimes become less feasible. So do you see that once we really have to fill these robots, soft robots will still represent a good solution in spite of all the challenges that field robotics present?
Yeah, so that's a good question. I think you might be making an underlying assumption, Marco, that the soft robot will inherently have more complexity or require more components than a more traditional robot, which I think is not true. The video that I wasn't able to really play of the archaeological robot, parts of that video show my student Margaret just piling the robot into a wheelbarrow, carrying it out to the site, having a very small portable compressor to provide the air, and essentially plugging it in and doing it in the field at high altitude, very far away from kind of the comforts of home. And so we've shown that it is possible to kind of put these into a space where I feel like maybe the complexity isn't necessarily very less, but at least the weight of the system is much less than a similar robot that might be able to be built, and maybe it wouldn't even be possible to have those same capabilities.
Okay, great. Thank you.
Hi, Allison. One of our questions from the audience, from Anonymous, is what kind of modeling approach can be used to apply to these growing robots, such as how to describe the shape changing, and how can these models be used for control?
Great, thanks a lot. You called me on my equation-free presentation. I think I didn't have a single equation in there. Yeah, absolutely. So let me just talk about the spectrum of answers. So then there's the soft robot and body intelligence people that say you don't have to have a model if you design it right. It's just going to do the right thing. But I'm not going to push that argument any further. There are many cases, of course, where you have to have a model. So, and then within those modeling methods, you have a huge range. For example, Christian Duriez at INRIA and collaborators have made very sophisticated finite element method or boundary element method models, which are computationally intense, but can accurately describe both stretchable and flexible types of soft robots. It does require quite a bit of kind of low-level mechanics base as well as computational knowledge to put those tools together in order to do those kinds of simulations. And they've done a fantastic job of making their work available to the world. And I think the world needs to catch up in terms of combining mechanics knowledge and computer science knowledge, which is not often taught to the same people, in order to make those types of models more ubiquitous. And another challenge that those models still have is interaction with contact with the environment and in context. Like you might be able to model one robot in free space, but it's more complex when you have multiple contacts. And then there's this whole range of more simplified models. One of the recent Robotics Automation Letters Best Paper Award honorable mentions is looking at more continuum models that are kind of based on simpler equations than finite element. They're like continuous models that can be used to describe how things bend. And those have been applied mostly to continuum robots like the type that I described. When you get to truly soft volumetric robots, then we still don't know, I think, how to extrapolate those models into that space. That said, the answer really is that there are many different types of models. I think to the level that you're willing to either have the expertise or to tolerate errors, people in the soft robotics community, they pick and choose different types of models. But almost all of the types of systems I've shown, we've had various different types of models that we've tried to apply to them. And most of them are not really used in low-level control, but rather what they're used for is to optimize a design process or to understand the function of the design.
Great, thanks.
I have a question for Mishank. Are there any research directions in soft robotics where microelectric mechanical systems are being thought of as an underlying building block?
Oh, that's a great question. So the question is about MEMS being the building block to soft robots. This is definitely not something going on in my lab, but of course there are many fantastic robotics group working on MEMS-based robots. I think the challenge is how there's, I say, two main challenges. One is challenges of scale, right? How do those actuators become integrated into a robot that is trying to operate at a larger scale, and can they be used as actuators, or can they somehow be integrated into sensors? As sensors, yes. As actuators, maybe not. Maybe the idea there would really have to be about what are new types of soft robots that are smaller and on the scale of MEMS, rather than trying to apply MEMS to this other scale. Another challenge that I totally did not highlight in my talk, because I was not referring to elastomeric soft robots, is that when you have very stretchy materials like elastomers and very soft plastics, their interface with the hard materials, which would be what a typical MEMS device would be created from, it's challenging to have that interface between something that's very stretchable and something that doesn't flex at all. And this is a constant challenge in building soft elastomeric robots. And so thinking about how a MEMS device wouldn't just rip itself out of something that's stretching a lot, I think is an open problem.
Okay, am I next?
I think Mengele is muted. mention?
Sorry, I'm not hearing a question.
Mark, feel free to, oh, sorry.
Yeah, so I have a question from an anonymous audience. This is related to the model question, but more general. So the question is, what is the theoretical framework and challenges for the Vine robots?
Oh, great. So for the Vine robot, I would say that at least in my research group, I don't think that we have a single theoretical framework. We have different ones. So for example, we just submitted a paper that's really trying to understand the shapes that can be achieved through tendon actuation. And it's totally geometric and kind of kinematical and all about just shape and not much about, say, dynamics or forces. On the other hand, we have another paper under review, which is trying to understand the dynamics of these Vine robots, because, and this is really an open challenge, which is that there may be some really useful behaviors that could be achieved by kind of ballistic motions. Like if you grow really fast, maybe you could grow across a gap that you would otherwise fall down into due to the weight of the robot. But understanding those dynamics so that you could shoot across would be critical. And for that, we've been trying to base it more on classical models like the robot equation. But I should say that because of the continuum nature of the robot, that is still a pretty challenging approach. So understanding shape, understanding dynamics, and how both of those can be integrated with control are open challenges, and maybe give a hint at the types of frameworks that can be used. But there's no one unified master framework that we're using here.
Okay, thank you, Allison.
Kind of following along the lines of the previous two questions, I'm wondering, so there are some clearly difficult issues with modeling and the theoretical aspects. You know, there's a reason why we do rigid body models, because it's easy. On the other hand, a lot of the robots that you build, I mean, there are some real hard design issues, getting them to actually work. How did you know, like the joint on the truss robot. The one question, a simple question is, which do you think is harder? And maybe another, just following on that, is more like, what can you give an example of, another example of the tricky design problem of, you know, what makes it hard?
Yeah, that's a great question. It's all hard, I guess. And then, and depending on how you frame the problem, maybe they can be made easy. But I would say when it comes to the mechanical design of many soft robots, there is the sort of optimization approach, or using something like the SOFA framework from INRIA, which I don't think I named my name earlier, where you can do very careful optimization in in a virtual space first, and then try to implement the robot. And that's one approach. But a lot of it is prototyping in the lab with glue and popsicle sticks. And for some people, that works really well. And that's actually been an interesting challenge for us. I've taught a soft robots for humanity class for freshmen at Stanford, co-designed with Laura Blumenschein. And in this class, our challenge was to take, the design approaches that are used by PhD students and postdocs in the lab, and how do you translate those to someone who maybe has very little or even no physics background. And for that, it's been a lot about how do you just define what are basic mechanical principles, which are advantageous, and how do you use those to create new ideas. And these freshmen came up with amazing ideas, and I should add a very diverse group of freshmen did this once they were taught just a few of the fundamental mechanical principles, which is a combination of understanding the mechanics and potential models, as well as having an intuition for how those things behave physically. So both of those parts can be difficult as you get more complex, but I think we have found ways to break it down in order to give people a good starting point. I'm not sure if that fully answers your question, so feel free to follow up.
Well, that was good. I have a kind of a one last quick, maybe it's a quick question. The kind of along along the lines of what Marco was saying, maybe a little bit more it's not so controversial, but maybe a little bit controversial, but just pushing things. On the truss robots, we have trusses usually because, I mean, in buildings and you know, in engineering, we have trusses because you want something strong, but lightweight. It's a frame rather than making
the structure.
Yeah, it's the structure.
Mm-hmm.
I'm worried that with a soft truss robot, do we lose something because it's soft in terms of the strength to weight ratio when we look at soft truss robots?
Yeah, absolutely. So that soft truss robot that I described as isoparametric robot, we're basically treating it like a rigid robot. We inflate the beams sufficiently that they are effectively rigid. And to the extent that they're not perfectly rigid, it's not going to be as structurally rigid and as kind of safe from that perspective. And the only place in that robot where the softness is good is the fact that these rollers can go along and bend it and change that kind of virtual joint location. So that's kind of the only plus, maybe the only obvious plus for softness in that robot. Otherwise, the softness there, I would say, is disadvantageous for a typical truss application. And so I think that trade-off, being able to have significant shape change, which you would not be able to have in a traditional truss, and even many traditional truss robots would also, you know, have some challenges, generating enough force on their actuators for you know, building type trusses. But that is probably the trade-off there. So the main advantage of softness is being able to create the virtual joints. There's maybe something about the compliance of the robot, but you're already saying you don't want compliance.
No, but I mean, the thing you also get is a huge range of expansion to compression ratio with the soft joint, which you cannot get with, let's say, a piston, which is really valuable. Anyway, I'll let other people go.
Yeah. Thanks, Mark. I should say Mark has designed some absolutely amazing truss robots, some of them based on a kind of zipper growing robot design, which has been very inspiring to our lab.
Thanks.
So I have another audience question from Chen. Do you have any suggestions or criticisms, to make it more provoking, for the direction of using deep learning for soft robotics?
Oh, that's a great question. I myself am not a kind of learning person, and I'm trying to get up to speed, but it's definitely not my training or my field. And indeed, we have been interested in understanding when and where learning is appropriate. So I feel like there's two places learning can be used. One, of course, is a very high level, like with any robot. And so without separately categorizing soft robots, all the ways in which learning is good and bad and challenging and helpful that occur with traditional robots also occur with soft robots. But I think the thing that's specific to soft robots is that the challenging mechanics, the difficulty of modeling the physics, the question is, when do you go to a learning method to understand those underlying physics of the robot? And that's actually something I personally struggle with. I'm not sure if my graduate student Nathaniel is watching right now, but you know, he recently proposed, oh, should we use learning for this aspect? And in that case, I was like, but we should be able to come up with like a real physics model in that case. And so I'm kind of pushing for us to come up with a model based on the mechanics. But that said, there are definitely going to be cases where it gets beyond our ability to really model and simulate. And in that case, the challenge becomes, how do we acquire the data necessary to do learning? How many times can we take a physical system and take data on its behavior in order to populate that model, whatever it is? We're typically going to need more data than most real physical robots are happy doing. maybe industrial robots can do it, but most soft robots are not really even purpose built to last in order to make that many, I guess, repetitions of movement.
All right, it's time to wrap up. I would like to thank you again, Allison, for her very nice overview of the field of soft robotics and for sharing her perspectives on a number of important items. Allison is actually one of the leaders of the robotics community, and she's going to have an open session on Thursday the 11th. So you may want to join that open session organized within ICRA if you want to talk to her directly. And in particular, if you may want to share with her some suggestions about how to make the robotics community more inclusive, better in general, basically following the discussion that Jeanette had at the beginning. I would also like to thank Mark for being our guest panelist this week. Next week, we're going to have another exciting talk by Anka Dragan on human-robot interaction. So we look forward to seeing all of you next week. Thank you, and have a nice weekend.
Thank you.